Well, I just started the recording, so let's get started. Today we're going to, if you cannot hear me, let me know. Otherwise, I'll keep talking. On the screen I shared, this is the 1, 2, 3, 4 topics we have for today. So today we have, that's our subject, started with 7, 8 of chapter 1, and then followed by 1, 2, and 3 sections on chapter 2. And also, I want to make an announcement about the labs. So we will start our first lab on this Wednesday at 11. So the lab, we're going to do it right here. There are so many new technologies. Some are not so new, but they start becoming popular. For example, the Zoom. So this is the tool we're going to use for the lab. I will also post it on Canvas. So this will be the tool. I would really like some feedback from you guys, because I actually watched my recording last week and the week before last week, and sometimes use this technology. What happens is, I assuming you guys can hear me. Actually, you guys all heard me pretty good for the Zoom meeting. But sometimes I was assuming you guys will see the exact same thing I was seeing on my computer. And when I was watching the recordings, I realized it's not always the case. Sometimes my screen share have a little glitches which not work as I was thinking it worked. So I was showing you guys something and talking, and it turned out nobody got it because you didn't see it on your screen. So this is what I am sharing with you is the tool we're going to use for our labs. It's called Multi-Sim Live. So in order to do this lab, everybody need to register for a free account. So right here, let's see. So what you need to do is do a Google search. You do a Google search on Multi-Sim Live. And basically you go there and register for a free account. Once you register for a free account, you are all set for this week's lab session. So we will meet on 11, and we will do a couple, maybe, simulations. This is all about simulation. It's a cloud-based simulation. So it's a very nice technology, but I wasn't using those. It has been many, many years, but because we actually have multi-sim in our lab, So instead of using this cloud-based, we have been using the real SIM, multi-SIM. We actually purchased about 30 licenses to use on our computers. So anyway, this technology is excellent. Multi-SIM is one of my favorite teaching program. It's excellent for electronics, excellent. So here we will do a couple of electronics simulations. Another simulation, another tool which became hugely popular is this. I'm using this also. It's called, let me show you. Yeah, you see, my type here is already on the search. So this is another popular, this guy, $200 device. It is an excellent tool for online teaching because it replaces not that almost 10 instruments. This is a simple box will replace almost 10 different devices. Let's see.
Dr. Zhang.
Mm-hmm.
So on this account, I just looked at my profile and it says I need to put in a serial number.
You just skip that because you are using the free version. Serial number if you want to use the professional, the real version on cloud. Yeah, we don't have to. Yeah, so everybody just use the free one. You don't need a serial number. Yeah.
Okay, can we walk through that again?
You just skip that part. You just close. You can just click on the create circuit instead of going to serial. You can have a free live.
Okay. Okay, so it's all about creating circuits on the software, and I can still make a circuit without putting in any sort of codes or anything.
That's right.
Okay.
Also, not just creating a circuit, you can do simulations. Also, they provide all the instruments needed to troubleshoot or to testing that circuit. It's an excellent tool. Yeah, I'm glad you're already there. So yeah, very easy. Just create an account. Do not type in any serial number. Okay.
Okay.
All right. That's about the lab. We're going to do that this week. The circuit we're going to do is also on Canvas. So if you look at the Canvas, this is your Canvas. I really don't like this. Yeah, this is the Canvas on the file. You go to the lab. You're going to this one, 452, section 2. And then you go to the files, week 3. And this will be a circuit we're going to simulate. I may add another one, a couple others. This is actually what we did last semester. This semester, because we are doing online, I'll probably add more right here this week, a couple more related to today's subjects. So any question about the lab? before we start the real class?
So, so we're going to be doing stuff on our laptops outside?
No, we are not going to meet in the parking lot this week. Excellent question. We just do it here because this is a cloud-based. When we meet a parking lot, we actually do some hands-on. So about half, I would say we might meet at the parking lot 6-7 times. The other 6-7 times we will do it here.
Okay.
So half and half, like a hybrid kind of lab. So we will do some hands-on, but this week is not meeting in person.
All right.
Thank you for clearing everything out. I hope everybody watched that video and watch this video and also. All right, let's get started. The first topic will be the continue. This is what we ended last time. Okay, now I need to switch cameras. All right, everybody see my document camera. So this is what we ended last time. We ended with a very important topic. I hope everybody remember. That's called the P and ID, right? P and ID. So that's what we ended last time, right here, P and ID. This P and ID is the most common diagram when we want to share our design. So when you complete a design in process control, what you do is you will communicate with your peers using this diagram. So this is one example of a P and ID diagram. It came from the old terminology, came from the old, like 80 years ago, because at that time, the process control is all about the piping. So you are connecting liquid and gas together, piping. And later, they have instrumentation. So piping and the instrumentation. Instrumentation means replace the pneumatic or mechanical device with an electronic device. So that's the word, instrumentation. So piping and instrumentation diagram. And the last time I remember I let you point you to page 619. This is everything about that diagram. There is a lot of details. I hope everybody, if they are reading a piping instrumentation diagram, you come back to this reference. If you have some questions about what every symbol means. So this has a very detailed descriptions of that standard. Okay, next topic will be the new topic. It will be the sensor response. So that's our first topic, sensor response. About all sensors, it takes some time to respond. And usually we call the sensors first order. So this is how the sensor responds. Let's assume it's a temperature sensor. So when you put the temperature sensor inside the oven, this is the response of your sensor. It's not instant response. So if you have an oven which is 400 degrees right here, that's a room temperature, and you put your sensor inside the 400-degree oven, it's called the first order exponential. So this is a mass representation. A lot of those sensors in the real world is just like that. So why is that important? Because we have studied this exponential in great details. So this is how the exponential goes. So when the sensor put in the oven, it goes like this. For the first order response, exponential, mathematically, we're interested in the 63% finish. 63%. Why 63%? It's all about math, exponential math. So we kind of just accept it, 63%. So 63% of finishing time. So this is, for example, room temperature. This is 400-degree temperature. Let's make it easier. This is 100-degree. I want to make it easy. So in order to make it easy, I will change 72 degrees here. So we started 70 degrees, ended with 172 degrees. So basically, you put a sensor from room temperature to 170-degree oven. So what is the 63%? That means the sensor reading will be 100. No. 72 plus 63, 135 degrees. So when you put your sensor to the oven, the reading will go up. If you put it long enough, the reading will be 172. But somewhere during that process, we have a reading called 135. How did we get 135? We just add 63. Because 63% of 100 differences, the difference is 100. So basically, you want this temperature go from 70, go up 100, the reading. But now it's not 100, it's only 63. That's 63% of 100. When the temperature reading is 135, that's 63%. That's timing. For example, if this is 2 seconds, this 2 seconds we call time constant. So time constant is something you want to know about the first order sensing. First order sensing. So all we want to know if your sensor is first order, and most sensors are first order response. So we want to know the time constant. That means 63% of finishing the measurement. Measurement is 60% there. So all you want to know is time constant. For example, its time constant is 1.3 seconds. They also give example of a sensor. The time constant is 1.5 seconds. So the manufacturer will provide you with this time constant. It turned out, once you know the time constant, how about the 2 time constant? This is 2 seconds. Another 2 seconds. What is the percentage here? 87. The percentage of 3 time constant. This is all math. And then how about the 5 time constant? So this is 5 tau. We use tau to represent time constant. So after 5 time constant, It's 99.3%. 99.3%. 99.3. And we consider that measurement is accurate enough if it's 99.3. So in this case, what is 99.3? That means it's a 72 plus 99.3 equal to 171.3 degree. So the reading after that is at 5 tau. If tau is 2 seconds, that means at 10 seconds. So at 10 seconds, your temperature sensor reading will be almost complete, 171.3 degrees. We consider that 100% because this little error, we just simply ignore it. So, for example, right now everybody checking temperatures. How long you have to wait if you put the temperature under the tan inside the. So when you want to measure temperature, how long you wait generally? Your body temperature. When you go to the doctors. Maybe 10 seconds, yeah. Or let's say 30 seconds. So if you go to the doctors, the doctor waits 30 seconds for your temperature reading to be accurate enough, represents your true body temperature. Then that implies the sensor the doctor used, the time constant is 5 seconds. 4 seconds. No, 6 seconds. So the time constant will be 6 seconds. That multiplied by 5 is 30 seconds. So as long as you hold your sensor in 5 tau, in this case 5 multiplied tau equal to 30 seconds, and then your reading will be accurate enough. So that is our first topic, the sensor time response. So you have to wait for 5 tau for your sensor reading to be accurate enough. How about I wait for 10 tau? Yeah, that's even better. But generally, when you're reading it, you want as quick as possible. For example, you are cooking something, you want the temperature reading. Yeah, if you can wait 10 tau, it's good, but 5 tau generally is enough waiting for the accurate. Let's do an example. For example, the sensor measures. This example is example 15 from our textbook. So sensor temperature reading is 30 milli per degree. The time constant is 1.5 seconds. My question number one: how long I have to wait to get an accurate temperature reading? It will be 7.5, right? So you have to wait a minimum of 7.5 seconds. Why? Because this time constant is 1.5. And when you multiply 5, that's 7.5. That's the minimum required. If you wait 10 seconds, that's even better. Doesn't hurt. So that's let's do the second part. After the input changes from 20 to 41, find the errors in temperatures. This represent errors temperatures. This represent at 5 tau. They also use a 1. Let's change it to 1.5 seconds. So that's the question. Start 20 degree and -41 degree. Tau equal to 1.5 second. At 5 multiplied tau, that is 7.5 seconds. Time sensor reading is 41 degree, right? Because at 5 tau, the reading will be complete for the reading. So my question, this is question number 1. Question number 2. At 1.5 seconds, what is the reading? What is the reading at 1.5? So we know 7.5, but how about 1.5 seconds? What is the sensor's reading? So let's do it. The sensor reading will be 63%. So what is 63% of the difference, right? That's 63% of the measured difference plus 20. So if we do the math, it will be 20 plus 20 plus 21. So we solve that problem at 1.5 second. The reading is 33.23 seconds. The author did another one. This is the temperature reading at half tau. This is not required because at half tau you need exponential. You need a more complicated math. We really don't want to get involved with all this. So instead, we do alternatively. We know it's 63%. So 63% means 13. So you add 13. You started with 20, and your measurement is 63%, which translates to 33 degrees. The second half of this section, not required. The reason we're not requiring this is because first, it's not that common. Almost all the sensors we dealt with are first orders. So that's reason number 1. Reason number 2 is the math is more complicated. It's exponential, but it's called second order exponential. So it's more difficult and not as common. So we just kind of skip that second half. Now we bring to our last topic for chapter 1. Last topic of chapter 1 is significant digits and statistics. It's 2 topics related to numbers. So first is significant figures or significant digits. What exactly are we mean significant digits? For example, this guy. That's 4. significant digits. 1, 2, 3, 4. So when you tell somebody the temperature is 33.23, you imply accuracy. That's your accuracy. So this last digit is accurate. So that's 4 significant digits. Another example, suppose you're buying a new house. What do you say? You buy a new house. 2,300 square feet. 2,300 square feet. That's significant digits. 23. 23. So that implies your house is probably somewhere between 2250 to 2350 square feet. Right? That's the accuracy of this implies. If the realtor tell you your house is 2310 square feet, that implies your house is more they measured it more accurately. So what happens if it's 2310.9 square feet? 2310.087 square feet. How many significant digits? This 7. 1, 2, 3, 4, 5, 6, 7. So is it really common? Nobody uses, right? Because nobody can build a house the square footage that accurately, build a square footage that accurately. Because when you measure it, it's impossible. It doesn't mean, so this is actually most commonly used. All the other, actually this is most commonly used. So 2 significant digits when you're buying a house. What about in control or general engineering? In general engineering, 3 or 4 is enough. Significant digit. So this is the conclusion of our first topic, significant digits. When you do a calculation, the final answers, you only need 3 or 4 significant digits. For example, if I ask a question, what does that equal to? You say that equal to 0.333. That's enough. That's enough. As final answer. So the reason for engineering we only use 3 or 4 significant digits is because everything we measure has errors, and that error actually accumulates. For example, you measure a house. It's 20 by 20. 20 feet by 20 feet. When you measure the 20 feet, no matter what kind of tool you're using, there got to be errors. And usually it's plus or minus 5%, for example. So the 20 feet you measured has errors. How about this? 20 feet has plus 5 errors, 5% errors. So everything has 5% or 1% errors. And so that's why any more significant digits doesn't mean anything. Just like here, you have 7 significant digits when you buy a house, but nobody will build that house that accurate. So this is not meaning anything. Even this is not used as often. We are 2,300 square feet or 1,000 square feet. My house is 11 11,000 square feet. That's all I care about. 11,000 square feet, for example. So 2 significant digits when you buy a house, a lot of time. And for engineering, 3 significant digits is enough. This is the first topic. Second topic will be something about statistics. Statistics is extremely useful subject because it's one kind of math we almost dealt with every day. So it's very, but we are not a math class, so we just have a very small part of statistics. So the statistics, there's 2 concepts we're going to introduce. Actually, we use it almost every day. The first concept is called average. The first is called average, or the mean of, if you have a couple of numbers, you can find in the average. Just like your GPA, the last letter A means average. So that's something everybody understand very well. The second statistic concept related to statistics is called standard deviation. Standard deviation, that's how we calculate standard deviation. This is a mathematical equation to find statistic standard deviation. And what exactly does it mean? So standard deviation means how those numbers are distributed. How those numbers are distributed. For example, your GPA. If your standard distribution, if your GPA is equal to 3.0, that's your average. If your standard deviation is 0, what does that imply? That implies every course you take, your grade is 3.0. So if you have 10 courses taken so far, all 10 courses are 3.0. So that's called standard deviation is 0. There's no standard deviation. So every grade is 3.0. So if your GPA is 3.0, your standard deviation is 1.0, that means a couple of your grade is 2.0, a couple is 3.0, a couple is 4.0 maybe. So you have this wider distribution of your grade. So this measures how wide, how variables varies from the average. So how about the third example? If your GPA is 3.0, your standard deviation is 2.0, that means a couple of your grade is maybe 1.0. Your average is 3.0, and a couple of your grade is 5.0. So you have a much wider or flatter, we call flatter. So this is a sensor A. The standard deviation is much smaller. So this sensor A is more accurate because when the temperature is here, your temperature sensor, the measurement is all very close to your average. The second sensor, the average reading is the same temperature, for example, but it's more flat. That means some sensor readings are far off, both above and below, far off from above and below the average. So obviously, sensor B is not as good as sensor A. If you just look at the average, you cannot separate the two sensors. But if you look at the standard deviation, you realize sensor A is more accurate. Probably it's more expensive also. So that's if the same price, obviously you want to grab sensor A because sensor A is more accurate and the reading is has a much less standard deviation. How do we calculate standard deviation? This is the equation. That's an example. So let's do this example. Example 18. So a temperature sensor read the temperatures 1, 2, 3, 4, 5, 6, 7, 8 times. So you read the temperature 8 times. That's the temperature reading from your sensor. What is the average? The average 1, 2, 3, 4, 5, 6, 7, 8. You add all 8 together, divided by 8. The average will be 21.6. So that's your average temperature. How about standard deviation? Standard deviation, you got this is how we do it. You subtract the average, subtract average, square it, and add them together, divided by 7, not 8, because we are doing 7 of those. Are we doing 7? No, actually we are doing 8. Yeah, we have 8 those components, but we are divided by 7. So we have 8 squares, 1, 2, 3, 4, 5, 6, 7, 8. That's the last one, 8th one. And we add them all together. We actually square them first and then add them together, divided by 7. So the standard deviation here is 3.04 degrees standard deviation. So that implies the accuracy of the sensor. Yeah. This is the average. This is your standard deviation. Let's do one more example. So if I have a temperature sensor, my reading will be 30 degrees, 31 degrees, and 33 degrees. What is the average? So the answer is actually 31.33333333. But we are not using, we are only keep 3 significant digits. So that's my answer. So the average will be 31.3. That's the average. What about standard deviation? To calculate standard deviation, 3 plus 1, 31 minus 31.3 plus 30 minus 31.3. All right, that's how we calculate standard deviation. We will subtract the average, started with first one, square, and then the second one, subtract the average, square, plus last one, subtract the average, square. We add them all together. Actually, on your calculator, see the calculator, we actually have a built-in function on your calculator. Let me see, my calculator. Mine do not have standard deviation. So the calculator came with my cell phone. Do not have a button set the standard deviation. Some calculators called statistic calculators have built-in function to find the standard deviation. That will help you a great deal because this is a real pain. If you type in all this using your calculator. But no, mine don't have standard deviation. Okay. So probably if you want to do that, you need another app. All right, that will complete chapter 1. Covered every topic, chapter 1. So it's a very important chapter, a lot of material. It's an introduction topic. It included math, physics, electronics, include a lot of things. Of course, most important is the concept. Is this figure 5 we have over here? This is the most important because that's the control loops we're going to study. After chapter 1, we will go to chapter 2 and 3. After chapter 2 and 3, we will start this 5, 4, 6, 7. So what is chapter 2 and chapter 3? Chapter 2 and chapter 3, we will go back to electronics. So some of you are electronics major, know a lot about this material. Maybe you already forgot, I don't know. So you actually take some classes, analog. And chapter 3 will be digital circuits. Digital. So 2 or 3, 2 chapters, they actually concentrate on a little bit of electronics because if you look at your control system, it's all electronics device, mostly electronics. You do have mechanical control or pneumatic control systems. Majority are electronics. So it doesn't matter even if your major is manufacturing, you need to know a little bit of electronics. So that's what we're going to cover start today from chapter 2. Anybody need a break? I guess nobody are having a camera turned on, so I'm assuming you guys are having breaks yourself. Because I can. Yeah. You want a break?
How long do we have to break?
Like 5 minutes. 5 minutes. I will pause it. Yeah, 5 minutes.
Okay. Can we do 10 minutes? Yeah. I wanted to run the Chick-fil-A.
Okay, run.
Okay.
Chapter 2, the topic is chapter 2 and 3. So we will have 2 chapters, chapter 2 and chapter 3. The 2 chapters we will talk about the signal conditioning. What exactly do we mean? So the first topic is what? What is signal conditioning? Signal conditioning, the author has 5 types of signal conditioning. 5 types. Type number 1 is called the signal level and the bias changes. So type number 1, we call the strength. Because a lot of signals we came out of the sensor is very weak. For example, 0 to 10 milli, that's, for example, one sensor. And that voltage is really low for the controller. And we want to convert that to 0 to 10 watts voltage, from 0 to 10 milli to 0 to 10 watts. So that's conditioning number 1. Or we want to convert it to 3 to 5 watts. That's another case. So we started with 0 to 10 milli, but in that particular example, or that particular controller or application, we want to convert 0 to 3, 10 to 5. So that's another. So that's called bias. Bias is also changed because the average here is shifted, 0 shifted to 3 instead of 0, still 0. So this involves signal level and the bias changes. Signal level and bias. So that's conditioning number 1. Actually, on Wednesday, our lab will be one of this lab exercise. We will design something to accomplish this. So we started with 0 to 10 milli. That's our original signal. And we will do a signal conditioning, type number 1, to convert the output to 3 to 5 watts, if that's what we wanted. And the signal conditioning number 2 will be linearization. Many sensors, the output is not linear. What do we mean? Not linear. That is what we mean. So this is your temperature, for example, and this is the sensor output. As temperature increase, the output is not straight. That's called nonlinear. And in most applications, we prefer the sensor output to be linear. This is a linear. So how do we go from here? That's where we start and ended up here, where we ended with a perfect linear output. So that problem is called linearization. That can be done, but obviously it's more complicated than the first case. So we'll talk about the second type. The third type of signal conditioning is called conversion. Conversions that involve current to voltage, pressure to current. There are many kinds of conversions. So also may involve analog to digital conversion. So this is analog digital conversion. So there are many different types of conversions potentially. That's another category of signal conditioning. The fourth type are called filtering. Filtering. So filtering is another important concept. That means some signals have extra components we do not want. some signal has extra components we don't want it. And how do we remove the unwanted components? Filter is one most common way to do it. So that's the fourth. The last one is called what is the last? Okay. Last is load matching. Electrical circuits, some can handle higher loads, some cannot handle high loads. Just like a mechanical component. So if your engine is 1 horsepower, it cannot used on your vehicle. 1 horsepower is not enough. So the loading capacity is not enough. Same for electrical circuits. Electrical circuits, some can handle high load, some can handle small load. So load matching is another category of signal conditioning. So we'll talk all about those 5 different types of signal conditioning in the chapter 2 and the chapter 3. So this is the first topic. What are we going to cover in those 2 chapters? So chapter 2 and chapter 3, we will cover 5 different types of signal conditioning. That's our today's first topic. Today, the second topic is how to do it, right? How to do it. There's so many different types of signal conditioning. We're interested in study how to do each type. We started with passive. We started with analog. Then we will do digital. For analog, we have active or passive. So we can do active signal conditioning, or we can do a passive signal for analog. How about digital? Digital, this subject is huge. It's called a digital signal conditioning. Most commonly, today, it involves a computer. Fortunately, today's computer costs pennies. So $1 computer, those are the most common components for digital signal conditioning, second type. What is the capacity of today's $1 computer? Today's $1 computer is extremely powerful, put it this way. Although it costs only $1, it's extremely powerful. Now, how about the computer inside your cell phone? How much does it cost? Low-end models, again, cost dollars. So if you buy a cell phone, costs you, for example, $300-$200, chances are the computer inside maybe $5 now. The newer models may be more expensive. The reason more expensive mostly is because the billions of dollars they put into research. To develop a new computer, it's very expensive because the engineers are paid how many digits? Engineers paid good, but the people paid most are the guys involved in the management, I guess, engineers. Anyway, so the digital, and today we will talk about this, passive. What is passive? Passive signal conditioning means RLCs. RLC. So we're only using resistors, inductors, and capacitors try to reconditioning our signal. Can we do it? Yeah. But it has limits. So that's why we have active. Active means RLC plus a very important component is called amplifier. So we added amplifier, which makes a huge difference. So this is much better. With the amplifier, majority of our signal conditioning will be active. But we start with simple, start with passive. So passive. Today we're going to cover 3 passive conditioning circuits. The first passive is called a divider. The second passive is called a bridge. The third passive is called RLC filter. So we will have 1, 2, 3. What is a divider? Divider is 2 resistors. What is a bridge? 4 resistors. What is RLC? It can be RL, RC, or RLC. This is 2, 3, or 4 components, right? RLC. So 1 resistor, 1 inductor, 1 resistor, 1 capacitor, 1 resistor, 1 inductor, and 1 capacitor. So those are 3 types of passive. So let's look at the first one, 2 resistors. That's how the divider works, 2 resistors. So this is a resistor number 1, resistor number 2. They are connected in series. And this will be my input, this will be my output. So divider circuit is extremely simple. It's just 2 resistors. And the input is connected to both resistors. So input is both resistors. Output is only connected to 1 resistor. What does that mean? The output will be a percentage of inputs. So the output will be the percentage of my inputs. That's a divider. So this divider, the output will be a certain percentage. How much percent? The percentage can be calculated using this equation, R2, R1 plus R2. So that is the percentage. That is percentage. So if I have a circuit, 10 ohm, in and out, the output will be how many percent? 50% of in. 50% of in, right? Half of input. Another circuit, 30 ohm, 10 ohm. What will be my output? Well, 10 divided by 10 plus 30 means 25%. So this is a divider. That's how it got named. It divide. So now the 100% will come out. Only in this case, 25% will come out. In this case, 50% of signal will come to the output. So you get a percentage. So this is divider. How about the bridge? Bridge, just remember, 2 divider. A lot of people make bridge so complicated. Actually, if you look at the bridge, it's a 2 divider. So that's divider number 1, divider number 2. So the input is right here. So we have R1, R2, R3, R4. So now we got 4 resistors. Look at this 4 resistors. That's divider number 1. That's divider number 2. What is the output of divider number 1? Right here, right? That's the output of divider number 1. What is the output of divider number 2? Right here. What is the output of bridge between the two? Between the two. So this is the out. So the output is actually the output of first divider and output of my second divider. That is called bridge. That's called bridge. Because we are looking at a river between these 2 points, right? We are looking at a bridge between the 2 points. So that's how it got the name. The bridge can be redrawn like this. These two are identical. R1, R2, R3, R4. So it's a look different, but it's exactly the same. So that's a bridge. What are the applications of bridge? Bridge is extremely popular. It has dozens of applications. The author listed a couple right here. So that's a couple of applications of bridge. Application number 1, lead compensation. What does that mean? Lead compensation. This is a typical process control example. Oh my God! So this is your bridge, and this is your sensor. So R1, R2, R1, R2. They call this R3 anyway. It doesn't matter. R1, R3, R2, R4. So the author used 1, 2, 3, 4. So that's what the author number doesn't matter. Yeah, we follow author's style, so no confusion. So R1, R2, R3, R4. R4, for example, is the temperature sensor 100 yards away. That's possible in a big factory. This is your control room. This is your location for your sensor. And it's 100 yards of long wire. If you look at 100 yards of long wire, that has resistance. So it will cause obviously problems. But by using a bridge circuit, this resistance doesn't matter. Why? This resistance doesn't matter? Because first, these 2 wires, the resistance is on both sides of the bridge. If the resistance 2, on wire number 1, wire number 2, wire number 3, there's 3 wires. The resistance of wire number 2 and the resistance of wire number 3 is identical because we're using the same gauge of wires. Because we're using the same gauge of wires, resistance is the same. So this resistance is the same, it cancels each other. on both sides of the bridge. They cancel. So that's called lead resistance cancellation. So it doesn't matter your lead wire is 100 yards, 200 yards, or 2 yards, or 20 yards. It's automatically cancel itself. Same thing for wire number one. Wire number one. Why wire number one cancel? Okay, wire number one, the two cancel. Yeah, I'm sorry. Wire number one and wire number two are both sides of the bridge. How about wire number three? Wire number three, the resistance doesn't matter either because that's only change the power. Like reduce the battery power a little bit. So it doesn't affect the reading of your temperature. So all resistance of all three wires doesn't matter. So this is very good. Cancellation. Application number 2 is a little bit of advanced, but we try to make it understandable. A lot of applications of a bridge is for the bridge. This is the bridge. Many applications of bridge are called a balanced bridge. So we want a balanced bridge. Balanced bridge. How do we balance the bridge? The bridge is balanced if, in this case, use this number. So 1, 2, 3, 4, right? 1, 2, 3, 4, right? The bridge is balanced if R1, R3 equal to R2, R4. That's the condition for a balanced bridge. That means the voltage here on the first divider is the same as voltage over there on the second divider. So these two voltages are the same. What happens if you have two identical voltage? That means the voltage here is 0. Oh, voltage here is 0. So we can hook up a meter. That's the meter. So if the unbalanced, the meter reading will be either left or right. When the bridge is perfectly balanced, the reading on the meter will be 0. The meter can be a voltage meter or current meter. It doesn't matter. It can be a current meter, this way or this way. Can be a voltage meter, this way or this way, same thing. But if the bridge is balanced, the reading here will be 0. That's called balanced bridge. The bridge is only balanced if these conditions are met. But what happens is R4 is a sensor. If R4 is a sensor, for example, temperature sensor, then that implies R4 will change with the weather. So right now it's nice and cool outside. I think it's in the 70s, 60s outside. Hopefully we can end our class earlier. Everybody go outside, right? But yesterday it's maybe 90 degrees, right? So this resistance always change. So that will throw the bridge off balance. Tomorrow, a cold front will come over. The temperature will be 50 degrees. And another day will be 90 degrees. So this resistor will throw the bridge off one way or the other. So how do we rebalance the bridge? You have to change one of those, or two of those, or three of those to rebalance. So by rebalance bridge, you need to change this, for example, or change R3. Only one it needs to be changed, or two, or three, but usually we just change one. Another way to rebalance the bridge is what the author put it here. So if this guy is the sensor, Yeah, 70 degree, tomorrow 90 degree, day after tomorrow 50 degree, the bridge will be off balance. Instead of change this resistance, the other inject another current to the bridge. That's an extra power. This extra power will be a current. And by alternating the strength of this current, we can rebalance this bridge. So that is a balanced bridge without changing the resistance, just using some circuit to inject different current.
I have a question about that.
This is more complicated than this. Why are we doing this? Because changing a resistor generally means mechanical. This can be changed by a computer or by electrical without moving parts. So this changing resistance involve mechanical moving parts. Generally, that implies unreliable situation. So by alternatively injecting a current without any mechanical parts or moving parts, this bridge can be balanced faster first. The computer or electronic device are much faster, and also hopefully last longer because no mechanical wear, no mechanical problems, potential problems created by mechanical device. All right, so that's application number 2. Let's do one more application. Application number 3 is for application number 3. All right, here. Application number 3, right here. We can measure resistance. Measure resistance. Application number 3. Application number 4. Not only bridges can be powered by batteries, the bridge can also be powered by AC power supply. This is AC power supply. In this case, we call it an AC bridge. So a bridge is not only can be DC, can also be AC bridge. So that's another application, AC. So why we want to energize our bridge using alternating power supply? Let's give you an example. This is an AC bridge. So when you look at the components, there are 2 capacitors, or an inductor and a capacitor. You can add inductors as capacitors, and this will be powered by DC bridge, AC power supply. And in this particular example, this particular bridge, I think it's called Maxwell bridge, but I can be wrong. But a lot of people develop a bridge, and that particular type of bridge is named after the inventor. So this bridge will be used to measure capacitance. So this is the capacitor. We do not know the capacitance of this capacitor. And then we can use this bridge to measure the capacitance of this capacitor. How to do it? We change the resistance to balance the bridge. Once the bridge is balanced, then we use this equation. Z2 multiplied Z3 equal to Z1 multiplied Zx. Zx is the capacitor we want to measure. That's the capacitor we're going to measure. And then we will just replace Z. This is Z1, Z2, this is Z1, this is Z3, this is Zx. Notice everything is given the only unknown is x, Cx. So by plugging all the numbers, that's the output. The Cx will be half microfarad when the bridge is balanced. So AC bridge has a lot of applications. Another application is measure the inductance of a coil. So many applications. The last application is actually the application we're going to use most often. That is, we are using bridge, the last application. We are using bridge to convert So we will convert resistance into voltage. So that's the most used application in this class. When we talk about resistance, we imply a sensor. A lot of sensors are resistive sensors. That means the output is a variable resistor. So it can measure temperature, can measure the flow, can measure the humidity, can measure the pressure. The output is a variable resistance. And unfortunately, the computers and the electronics do not like variable resistance. It prefers a voltage signal or a current signal. So how do you convert a variable resistance to a voltage? That is using a bridge like this. Using a bridge like this. So when we're using a bridge like this, that's the sensor. So when the sensor resistance changes, that will be the variable voltage. So when the sensor resistance changes, it will throw our bridge off balance. The further away the resistance changes, the further off balance. The further off balance, the higher the voltage here. So the output is a voltage, the input is a resistance. So this is a variable resistance, this is output voltage. And the author used the graph. So that is the resistance of my sensor, that's the voltages. So notice, if the resistance is 100 ohm, the output is 0. Right here, 0. So horizontal is resistance, vertical is output voltage. So at 100 ohm, that is the perfect balance. The bridge is balanced. What happens if the temperature goes up and down? The resistance will change to, for example, 150 ohm. Then the output is off balance. It's a negative output voltage. So when temperature goes up, the output will be negative voltage. When the temperature decreases, the resistance will drop, and the output voltage will be positive. So when temperature goes from, for example, 50 to 90 degrees, this is 70 degrees, and this is 50, this is 90 degrees, and the output voltage will go up and down. Notice this is not linear, But fortunately, usually the temperature measurement is limited to a very small portion. The temperature, the resistance variation is not dramatic, goes from 0 to 500, for example. Usually its resistance only changes from 80 to 120, for example. So minimum is 80 ohm, maximum will be 120, or 90 to 110. So if the resistance only varies This is the 190 to 110. And then we look at this small portion. It's almost perfectly linear. So even though it's not linear, but if the resistance is a limited change, plus or minus 10 ohm, plus ohm or minus 10 ohm, then in this range, it's almost perfectly linear. So that's the last application. I hope everybody remember the last application. It's called convert the sensor, which is the resistance, into an output, which is the voltage. And the nice thing about it is it's linear, almost linear. Yeah, that's the good news. In most applications, it's almost linear. And that is what we wanted, almost linear. Let's move on to the last topic for today. Hopefully we end it in about 15 minutes. The last topic of today is called the filters. There are so many filters. The design of filter is not our subject. This is not intended for a class to reteach our electronics to everybody. That will be another class. But here we want to cover is the different types of filters. Different types of filters. Low pass, high pass, band, pass, and band reject. Band reject. So those are the 4 types of filters. 4 types of filters. This is low pass, high pass, low pass, and high pass, and band pass, and band reject. Band reject. What exactly is a low pass filter? This is called a Bode plot. Bode plot is the most commonly used plot when we talk about filters. So we use Bode plot. So Bode plot is used most often. So a low pass filter looks like this. A low pass filter. So very intuitive. That means this is called cutoff frequency. Cutoff frequency. F cutoff. Cutoff. For example, the cutoff frequency is 1000 Hertz. So we call this low pass filter. Anything below 1000 Hertz will able to pass. Anything above, any signal above 1000 Hertz will be rejected. Reject. So low pass, high reject. Yeah. The second filter is this. And this is called cutoff frequency. Cutoff. This is pass, high pass, high pass. If the cutoff frequency is 10,000 Hertz, so if your signal is 20,000 Hertz, it will pass. 20,000 Hertz will pass because the cutoff is 10,000. If your signal is 5,000 Hertz, it will rejected. So the output, there's nothing. There's nothing. Because the signal is blocked. How about bandpass? Bandpass is this. And there's two cutoffs. You have a low cutoff. You have a high cutoff. And between the low cutoff and the high cutoff is called bandwidth. The bandwidth is the difference between the low cutoff and the high cutoff. Let's give an example of a bandpass application. Let's assume I'm listening to a station called 89.3 megahertz. So I'm listening 89.3 megahertz. That's a station. Low cutoff is 89.2 megahertz. High cutoff is 89.4 megahertz. So what is the bandwidth? High cutoff, low cutoff, bandwidth is 0.2 megahertz. Usually we don't use 0.2, we just use 200k hertz. So that is the bandwidth of this radio station. All FM radio station has a bandwidth of 200k, 200,000 hertz. So that's one station. There's the second station is called 89.5. The third station will be 89.7 megahertz. So those are the station carrier frequencies. So when you listen to this station, you need a band pass filter. The bandpass, because you don't want noise from adjacent channels, adjacent stations. You don't want to hear this, you don't want to hear this. You only want to hear the voice from that particular station. And how do you do it? Use a bandpass filter. How many? You use it 10 times. Actually, if you look at a typical radio design, generally, you have 10 of those filters because you really want to concentrate on one station. You don't want anything from neighbor stations. So you use that's called a super hat radio station. Previous semesters, we have a 342. That's a communication class. We talk more about that. But anyway, that's a bandpass. The last filter will be band reject. What is the band reject? It will be look like this. Low cutoff, high cutoff. Between the two is called the bandwidth. This bandwidth can be narrower or wider, depending on your applications. But that means any frequency started at the low cutoff, ended with high cutoff, will be rejected when you signal trying to pass through. So band reject. So if low cutoff is 1 mega, high cutoff is 2 mega. So if your input signal is 1.5 mega, there's no output. Why? Because this 1.5 megahertz is just inside this trap. Inside this trap, so there's no signal. And if it's 10 megahertz, 10 megahertz came out. no problem, because 10 megahertz is way outside your trap. The further away from that trap, the better. The closer, potentially you have potential loss. This is what are the filters, but how do we do it? How do we do it? Very complicated. You can design very complicated. You can also design that called a digital filter, digital or analog. So there's two ways to do a filter. Number one is analog. Number two is digital. The two ways to do a filter. The digital is actually more common because right now everything is digital. When you listen to music, it's music on your cell phone is digital. So digital is a computer solution. How about analog? Analog, there are many, many analog filters because the filter is so important. Past decades, huge amount of research or development is concentrated on that. So there's so much filters, so many of those. How about the simplest? This is the simplest low pass. Simplest. Can be very fancy, can be very sophisticated. But this is the simplest low pass called RC low pass. What about the high pass? Simplest high pass. RC. What about the band pass? Simplest band pass. What about the band reject? Simplest band reject. So those are the simplest. So just in case you want the simple ones, you can experiment. A couple of semesters ago, one of our graduates, he actually really hands-on. He was working in the labs. He was working on a simplest RC filter, low pass, simplest low pass RC filter. And he had so much fun just on these two simple circuits. So he experimented the in and out, change the capacitors and resistance, and just two simple circuits. And you can experiment what's the input and output. We will have a lab this Wednesday. Maybe we will do one of those. Yeah, I'm still working on it. So we will meet Wednesday at 11, right here on Zoom, not in the parking lot, right here on Zoom. And please do this after class. Please do this after class. Go to this website and register. Yeah, go to here. Go to this website. Right here.
Oh, we can't see it.
Go to this website. Somebody talking. I heard somebody talking. I put on my earphone.
Oh, I said we can't see it right now.
Can't see it right now. Thank you for the feedback because let me see what's wrong.
Yeah, we're going to see those more hands-on in the future, right? Because I don't know, I'm starting to get lost.
You mean meet in person in the lab?
Yeah.
Yeah, about half will be meet in person.
Okay.
So go to this website. Now you see, right?
Yes.
All right, that's the website. And the register is called Multi-Theme Live. Google it, Multi-Theme Live. Google it and register for free Multi-Theme Live. There is a paid one. You need a serial number. We don't have a serial number, so just skip that part. Then you have a free Multi-Theme Live. It's a cloud-based application, so you do not have to install any programs. It's on the web browser. The application is on web browser. All right, any questions? Why you lost? Who is talking about lost? I really want to know because that's really, I'm still learning how to do it better. I watch my videos. I'm trying to figure out how to make it better. But you think you are lost? That's a good question. Good point. Craig, are you talking about lost?
Oh yeah, I was just saying that I don't know, just seeing it on paper and in diagrams isn't the same as actually seeing these actual devices being used.
Oh yes, yes. So
that's all I meant.
Okay. Yeah. Like I said, everything is going online, like video. This tool is this is my favorite tool, Multi-Theme teaching tool. But I really got it, nothing compares with a hands-on. So we do meet about 50% in the parking lot. So 7-8 times.
All right. I look forward to that.
Yes, and see everybody's face. Of course, you need to cover the face. Fortunately, I will cover the whole face. That's true. It's called face bikini. Face bikini. You heard about that? I stopped recording first. Stop the recording. Stop the share. Yeah. Any else? Any questions? I will stop recording.
I've never heard it called that.